We view modern cities and human engineering as a pinnacle of innovation. Yet, long before we learned to stack steel and wire circuits together, the natural world had already perfected its own forms of complex technology. This timeline chart compares the common goldfish memory myth against actual behavioral data. The bottom bar shows the reality. Goldfish retain complex spatial information and successfully navigate mazes for months. In laboratory settings, these fish demonstrate a clear sense of time. They can be trained to wait and press a lever at precise scheduled intervals to receive food, proving they possess high-level temporal awareness. Moving from the water to the sky, crows demonstrate cognitive problem-solving skills comparable to those of a human toddler. They memorize and distinguish specific human faces. When placed in controlled lab tests, they even bend straight pieces of wire into functional hooks to extract hard-to-reach meals. If common suburban wildlife possesses this level of cognitive processing, the deeper wilderness hides biological engineering that borders on science fiction. Millions of years before humans developed indoor climate control, insects were already building self-sustaining skyscrapers. Termites construct massive mounds that act as self-regulating systems. Without using electricity, these insect engineers precisely control internal airflow, humidity, and temperature. Early human HVAC setups, like this vintage General Electric window unit, achieve through mechanical power what termites accomplish using dirt and biological instinct. Under the ocean, the common barnacle manufactures an industrial superglue that outperforms our best synthetic adhesives. This biological cement cures underwater, resists salt corrosion, and bonds to surfaces on a molecular level. Human shipping companies spend billions of dollars every year trying to scrape this stubborn cement off steel hulls and propellers. Despite our manufacturing capabilities, heavy industry still struggles to synthesize a material that matches the durability of nature's baseline models. Navigating vast, hostile environments requires high precision, especially when visual aids are removed from the equation. Bats map their surroundings using echolocation, emitting high-pitched sounds that bounce off physical objects. This creates a sonic topography that allows them to hunt fast-moving insects in pitch darkness. Human engineers arrived at a similar solution decades ago, building massive metal radar arrays to bounce radio waves off distant objects. Meanwhile, creatures like the star-nosed mole and the platypus utilize electroreceptors. These biological sensors act as living metal detectors, allowing them to hunt by feeling the faint electrical fields generated by hidden prey. Above ground, wolf packs maintain a howling network over miles of dense forest. Each wolf's voice is unique, allowing the pack to track individual locations and synchronize group movements. This functions much like a squad of soldiers maintaining contact through handheld radio transceivers. The wolves broadcast on a highly calibrated biological frequency. The natural world operates on a dense network of high-tech sensory frequencies that humans have only recently managed to replicate. The wild is an unforgiving environment with life or death stakes, requiring prey to deploy biological weaponry and stealth tactics to survive. This bombardier beetle cross-section shows real-time chemistry defense. It holds two distinct reactive chemicals in separate chambers. When threatened, it mixes them on demand, firing a boiling 100 degrees Celsius directional blast straight into a predator's face. Other animals rely on systemic suppression. When an opossum plays dead, it undergoes an involuntary physiological shutdown. Its heart rate drops and its body goes entirely limp, causing predators to lose interest in what appears to be rotting prey. In the ocean, cuttlefish manipulate thousands of pigment cells to alter their skin texture and color in milliseconds, achieving flawless cloaking against any background. Survival in these environments demands the successful execution of chemical engineering and real-time active camouflage. Sophisticated navigation and communication systems existed millions of years before the first human patents. Many of our modern technical achievements mirror solutions already perfected by evolution. The honeybee's waggle dance functions as a precise coordinate system for the entire hive. This geometric vector map shows the dance in action. The angle of the insect's body relative to gravity dictates the direction of the food source in relation to the sun, while the duration of the waggle communicates the distance. These organisms are the most successful engineers on the planet, standing as the final result of a research and development process spanning millions of years. Every organism in the natural world operates as a piece of rigorously battle-tested living technology. Thanks for exploring with SciFacts Info. Keep questioning the world around you, because the answers are usually hidden in plain sight.